Hi, my name is Sydney Cumby, and this is my PHYS2212 Lab 3 circuits. So, for the purpose of this lab, it was to predict the behavior of circuits containing resistors in series and parallel. Use multimeters to measure the actual values of conventional currents and potential differences in the circuit, and examine the behavior of ohms, restrictors, and capacitors. Within this experiment, the system was the whole circuit, and the surroundings was everything else within the experiment. Our results showed to see that the delta V I got was originally 0.1, but should be 0 due to Kirchhoff's law. By increasing the resistance in the RC circuit, we increase the time charging the capacitor and the diminish of the light bulb. So first I'll start with some fundamental principles I used within this experiment. The first one being Kirchhoff's voltage law, which is the sum of the voltages within a loop is equal to 0. The second one I used was Kirchhoff's current law, which is the sum of currents in equals the sum of the currents out. I also used capacitance, which is the charge is equal to capacitance times voltage. And then Ohm's laws, which basically shows the relationship between volts, current, and resistance. So, to set up our experiment, we had two 1.5 volt batteries and then two 45 ohm resistors, and we connected our amp meter at I1 and I2, shown as the image on the left, while in the image on the right, our amp meter displays 0.01. That is incorrect, as when calculating with Ohm's law, we should get 0.03 amps. During our experiment, we had the settings of our multimeter messed up. That was just human error, but as shown through Ohm's law, it should be 0.03 amps. So now we're going to talk about the voltage within the circuit. So as you can see on the left side, I have them all labeled A, B, C, D, E, F, G, H. And the voltage from A to B is going to be 3 volts. The voltage from B to C was 0 volts. C to D was negative 1.5 volts. D to E was 0 volts. E to F was negative 1.5 volts. F to G was 0. G to H was 0. H to A was 0. So the summation of all the volts was 3 volts minus negative 3 volts, or 3 volts minus 3 volts, which equals 0. And then in the right side, you can see how the voltage spikes on different parts of the actual system and around the circuit as it increases and then decreases back down to 0. Okay, so after the voltage within the currents, we now are talking about the RC part of the lab. So with this, we're going to be testing the charging of the capacitor and the discharging of the capacitor, and basically how long it takes for the light to diminish. As you can see on the right side, the image, that was us charging the light and making it shine after charging the capacitor. So the amount of time for light to diminish we found was 11 seconds. This was not very correct when doing the analysis of how much the decay should be. A few sources of error. This could be incorrect capacitance value, errors in starting and stopping the timer. We did have a few problems starting it exactly when the light bulb shut on and turning it off exactly then. Either way, this should have been a little bit faster than 11 seconds. So lastly, we have our what if. What if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain. Okay, so within an ideal model in circuit, if the capacitor is charged without a resistor, it would reach full charge instantaneously. This is because when resistance is 0, the loop and voltage also must equal 0. So it implies that the capacitor will fully charge the moment that it's connected to the battery. But in reality, the capacitor does not charge instantaneously as shown by this experiment, because all circuits contain some resistance, even if it's very small. Just like the battery, the wire, the capacitors itself all have resistance. So it limits how quickly the current can flow. But as we can see, the capacitor still charges quickly, but just not instantly. Thank you so much and have a good day.